After discussing the oxidation number, where we have realized that there are certain rules that are used to determine oxidation number of different atoms, of which the oxidation number of a compound is simply the sum of the individual oxidation number of the constituent elements making up that compound. We have used that concept to calculate oxidation number of various elements, and it is this that help us to understand the reason why sulfuric acid is given the IUPAC name sulfuric 6 acid, nitric acid called nitric 5 acid. Finally, we also concluded that increase in oxidation number is known as oxidation, and decrease in oxidation number is reduction, and that happens in redox reactions. In this lesson, I want us to talk about electrochemical cells. When a piece of metal is placed into a solution of its own ions, the metal rod ionizes. Hence, the electrons are released, and that will give M metal from solid ionizing to give M ion plus the same number of N electrons that are lost. The electrons released remain on the surface of the rod, while the metal ions get into the solution, hence this diagram. So we have this is a solution containing metal ions. Then we place this metal rod this is solution of metal ions. So the metal will go into solution after ionizing, and that is what will going to be obtained. As the negative charge on the metal rod increases, the positively charged ions accept the electrons to form the metal. So what will happen in the solution is that the positively charged form ions will gain the electrons to form the metal. As the rate at which the metal ionizes increase, the rate at which the ion gain electrons to form the atoms also increases. This will happen eventually, and the two reactions will occur at the same rate. Hence, an equilibrium will be realized. M giving M ion plus N ion, and that will give now the equilibrium, whereby M can undergo oxidation to form M ion, and that can lose to give back the solid. As this happens, a potential difference is created between metal rod and the positively charged ion in solution. The concentration of electrons on the metal rod can be measured and this is known as electrode potential. This arrangement of a metal rod dipped in a solution of its own ion constituents constitutes a half cell. So we are saying the arrangement where a metal rod dipped into its own ion constitute a half cell. A half cell is represented as metal stroke metal ion. For example, copper half cell is represented as copper solid getting into copper ions. The tendency of a metal to ionize when in contact with its own ions differs from one metal to the other. The difference can be determined by connecting two different half cells to make a full cell. The two half cells are constructed in such a way that the metal rods are connected by a conducting wire. Are connected by a conducting wire which passes through a voltmeter that is used to measure the electrode potential. The two solutions are connected by a salt bridge. The two solutions are connected by a salt bridge. Where the salt bridge is in form of a filter paper soaked salt bridge, which is in form of a filter paper soaked in a saturated solution of either sodium nitrate or potassium nitrate. The diagram below represents such cell. Let's have the representation of such cell having two different solutions. So this is solution, metal rod connected to another metal rod, voltmeter. So this is X and this is element M, metal M, and as you can see is dipped into its own iron, that is M iron, and this is also dipped into its own iron. So this is X ion. This is a solution of X, a solution of metal M, and the two are connected. The two solutions are connected by what is called a salt bridge. So this is the salt bridge, which is a paper dipped in a solution of potassium nitrate or sodium nitrate. The difference between electrode potential of the two electrodes is referred to as electromotive force. So this is the diagram, and we are saying that the difference between electrode potential of the two electrodes is what we call electromotive force. EMF of the cell. The EMF is measured in volts using a voltmeter. Measured in volts using a voltmeter. Examples: when zinc, solid zinc ion, and copper, solid copper ion are connected, they result into a full cell, and the following observations are made. Following observations are made. The first one, at the copper 2 ion, the intensity of the blue color of copper ion decreases. The intensity of the blue color of the copper 2 ions in solution decreases, and the brown solid is deposited. Another one, brown solid is deposited. That is the observation made there. At the zinc ion, the zinc rod wears out. The voltmeter records a reading of, another one, the voltmeter records a reading of plus 1.10 volts. From the above observations, we realize, let's look at the explanations. That at copper ion, there is a gain of electrons. The first one, at copper solid copper ion, we have copper 2 ion gaining electrons, to form copper solid, that is copper 2 ion undergoing reduction to give copper solid. And it is the copper 2 ions responsible for the blue color. So the moment they have gained electrons to turn to copper solid, it means that there is no blue color at all. So that is the reduction process. Then at zinc ion, we have zinc solid oxidized to zinc ion. And that's why it wears out. So that will be zinc solid undergoing oxidation to form zinc ion, and during that there is loss of 2 electrons, and that is another half equation, and it is because of this that we are saying that the zinc strip will wear out, because it will go into the solution. This shows oxidation. Remember, what we said in our previous lesson is that oxidation is increase in oxidation number, and reduction is decrease in oxidation number. So this is the reduction process, and this is the oxidation process. From the above equation, it is noted that zinc rod has a higher tendency to form ions when in contact with its own ions in solution as compared to copper rod. Therefore, the zinc rod ends up with a higher electrode potential compared to copper. This makes the zinc rod to be negative, relatively more negative than copper. And when the two cells are connected, the electrons will flow definitely from zinc rod through the connecting wire into the copper ions. This explains the reduction at the copper ion and oxidation at the zinc ion. So when we connect the two half cells, now this general equation that you are going to have, overall equation, will have copper 2 ions plus zinc solid. Remember, copper ion is undergoing reduction, so that will give copper solid, and then zinc is oxidized. And we said that the E value is plus positive 1.10 volts. From the equation, oxidation takes place here. There is oxidation, that is zinc ion, and reduction takes place at this electrode, copper ion, that is reduction. The diagram for this cell is drawn as follows. So we'll have the diagram representing this cell. That is that we have a metal strip. So this is zinc iron. This is copper 2 iron solution. So we have connected to the voltmeter. This is zinc rod, and we have copper electrode or copper strip. And then these two are connected with a salt bridge. Salt bridge. So this is the diagram showing how electrons will flow. Definitely electrons are lost this side, where zinc is loose, and then electrons will flow to be gained the other side. The above cell can be represented, and the representation is as follows. First of all, you have to know that salt bridge, when representing a salt bridge, we use those parallel lines or a single broken lines. That is to represent a salt bridge. Therefore, cell representation will be as follows. Zinc solid being oxidized to zinc ion, salt bridge. Then we have copper 2 ions reduced to copper solid, or we can have before that, this should have a side. You include the E value. E is equals to plus 1.10 volts, or zinc, sorry for that, this should be a single line separating the two, and then the state symbol is very important. So this is zinc solid giving zinc ion, then salt bridge, broken line, copper 2 ions reduced to copper solid, and the E for that is plus 1.10 volts. Question: copper solid to copper ion and magnesium solid magnesium ion half cells were connected to make a cell. A voltage of plus 2.04 volts was recorded. On the voltmeter. A. Draw the cell diagram for the above cell. So first of all, we'll have the diagram drawn. So this is the solution. This is solution of magnesium. Then the other side is a solution of copper. So we have salt bridge, also will connect them. That is magnesium electrode, copper electrode, these are copper 2 ion. That's a solution of copper. This is a solution of magnesium. Then there is a salt bridge connecting the two solutions. It has to be dipped into the solution always. So that is salt bridge. Voltmeter, and the flow of electrons is also indicated. So that is how the diagram will look like. Part B, before we go to part B, it is clear that that salt bridge must be always dipped into the solution. Should not be left hanging like this. Must be dipped into the solution. The salt bridge has to be dipped in the solution in all cases where there is drawing of salt bridge, you have to ensure that the salt bridge is dipped into the solution. The two solutions, and that is the essence, just to connect those two solutions. And that is why it has to be dipped in the two solutions. Our next question is write part B write the cell equation for the above cell. So now, magnesium is more reactive than copper, and it will definitely reduce the copper by undergoing oxidation. So there is copper ion plus magnesium solid and that gives copper solid plus magnesium ion, and you can see the E is equals to plus 2.04 V. So there is oxidation and reduction, whereby this is oxidized, that is oxidation process, and this is reduced, so that is the reduction process. And last question, write the cell representation for the above cell. Cell representation for the above cell. So writing cell representation, we start by writing down what is undergoing oxidation, then salt bridge, and finally what undergoes reduction. So that is magnesium forming magnesium ion, salt bridge, copper 2 ions to copper solid. This is aqueous solid. E is equals to plus 2.04 volts, and that is the whole question. When the electrode potential is positive, it shows that oxidation occurs in the half cell connected to copper ion. NB when the electrode potential is positive, it shows that oxidation occurs in the half cell connected to copper ion half cell. Therefore, when drawing the cell diagram, that particular half cell has to be drawn on the left hand side. On the other hand, when the electrode potential is negative, it shows that oxidation. So on the other hand, when the electrode potential is negative, then it shows that the copper ion half cell as oxidation has oxidation taking place or undergoing oxidation. When the electrode potential shows the oxidation occurs in that half cell while reduction occurs in the other half cell. Therefore, when drawing in this case, the solid copper ion must be on the left hand side of the diagram. Below are some electrode potential obtained when copper ion half cell is connected to other half cells. So summary of electrode potential. So we have metal ion half cell, then electrode potential. In volts. So the first one, magnesium ion, they will say that is plus 2.04. Zinc ion, they will say that is plus 1.10 volts. Iron to iron 2, that is plus 0.78. Lead to lead ion, that is plus 0.47. Copper to copper ion, since it's the reference, 0.00. And finally we have silver to silver ion, that is minus 0.46, indicating that silver is less reactive compared to copper. Finally, let's discuss functions of salt bridge. Number 1, complete the circuit. By making contact between the two solutions. Maintains charge balance. In the solutions. By providing ions to replace those ions used up or those formed in the solution. And those are the two functions of salt bridge, which marks the end of the discussion, electrochemical cell.